All right, class. Just one or two assignment discussion. The first question we have already done it in the class, this one. And the second question here, a hollow cylindrical conductor, this one. This is very much similar to the first one. What will be the difference here? The outer part is like this, and there is a hollow inner part as well here. And two radii are present. One radius is B and the shorter radius is A. So see, when you take the area, this becomes pi r square you have. So that becomes B square minus A square. This is how you get the area for it. So like in the previous question, it was just I A square is giving you I. So you got it for unit, that was I by pi A square. And then you got it for r square, correct? So here also this will be r for r square minus a square. How much will you have? For this much is giving you the current I. So unit area will have I by pi b square minus a square. So how much will the area pi r square minus a square have? You just have to multiply, class. You will get obtain this as it is, and same question, same it's there. So this was there in this question to be done, and first one was exactly what we have done. Coming to the solenoid one, see, it says a 50 centimeter long solenoid has 4 layers of windings of 350 turns each. The number of turns are given. It says the radius of the lowest layer is 1.4 centimeters. So radius is given, current is given, magnetic field near the center of the solenoid, near its end, outside. See, near the center, the formula will be B is equal to mu naught Ni, which we have studied. The second part, near its end, the formula for near its end, this we didn't do it in the class and it has come in the exam. This will be mu naught Ni divided by 2. And last, outside the solenoid, it is 0. So that was the answer. So once this came in the CBSE exam, okay, near its end we haven't done. This is important. This near its end is mu naught Ni by 2 for the long solenoid. So you write it somewhere that the magnetic field at the end of the solenoid will be mu naught Ni divided by 2. Then this is a similar question. At this here you have to calculate 0.1 centimeter from the axis of the wire at the surface of the wire and a point outside. So same thing. Here you are going to use this formula. When you're calculating at the surface will also have the same formula, but this is outside, it will again become 0. Okay, regarding the force assignments, that I'm not discussing because none of you have given the force assignment. So share the force one, then force between force due to the motion of the charged particle, that we'll discuss. Coming to the chapter, back to the chapter, force between two parallel wires we have done. Zainab, you're joining after a long time. What happened? Exams are going on. No, now you must have the vacations then. Yes, yes, Zainab. Am I audible to you, Zainab? Is it audible, Muniba, Zainab, to both of you? Okay, you are traveling. All right. See, we have come. Zainab, do take the class notes at least from the video lectures. Okay, or take the class notes at least. So you'll have the materials at least with you. So we have completed this entire topic now. Current carrying coil as a magnetic dipole. This question. When the wire has the coil is present, okay. Before going to the magnetic dipole, there's a concept which will be utilized in this chapter, in the next chapter, and the chapter EMI especially. How to get the direction of the current when you know the polarity, or how to write the polarity when you know the direction of the current. So see, if you know the south polarity, let's just do one thing. Just draw an S in your device like this. Just draw an S like this. Then mark the arrows of the S. Just make parallel arrows to the S like this. See, which direction is this? This is clockwise. So that becomes the direction of the magnetic dipole. That's how you have to check the direction of the current. Whenever you have the south polarity, the best way, for especially for the circular arcs. For square also you can do this. Same thing you can apply for the squares also. If you have a square, just put an S. Just get the directions of the arrows using this. Let's say the north polarity. Mark an N here. Make arrows over here. And besides these arrows, just make the parallel arrows on the main figure. Look, this is anti-clockwise. So this is giving you the direction of the current, when you have the polarity is given. So two things are there: polarity giving the direction and direction giving the polarity. All right. So this is a very easy concept which isn't used. We'll be discussing the formula of the magnetic dipole. Best part is that you don't have the magnetic dipole moment in your syllabus separately. So what we'll do, we'll just have the formula. Magnetic dipole moment is equal to current multiplied to the area. No derivation for this, straight away remember the formula. What is it? M is the magnetic dipole. Like you had the electric dipole, what was the formula of electric dipole? Yes, class, formula of electric dipole moment. What was it? Formula of electric dipole moment, you have forgotten? This is the fourth chapter. Yes, Muniba, you must, do you remember?
Q into D.
Yes, Q into the length separation between. But this is different. That formula, similar formula to that we'll do in the fifth chapter. Okay. So this is definitely the area of the coil. So if n number of turns are there, you have n number of turns, then you definitely write the formula as m is equal to NIA. Multiply it with the number of turns. Now, how to write the direction? Okay, when you have it, simply what you do, you use your right hand thumb. Okay, you just curl the fingers the way the current is moving. Whichever was the direction of magnetic field earlier will be the direction of the dipole moment. How did we study earlier that if it is moving clockwise, we'll curl our fingers clockwise, thumb is pointing inwards, that's it. Here also anti-clockwise, thumb is pointing outwards, that's it. Same direction will be for the magnetic dipole moment. That's what has been written. Curl the fingers along the sense of the current, the thumb will definitely give you the direction of the magnetic moment. Okay, so this is about the magnetic moment. We'll practice these questions. These two questions we'll practice. Do one thing, write them. Write these two. Write down the formula. Okay, let's come to the question. So see, usually the figures will be given to you like this, and it's very easy. See, when it's a circle, you know the area of the circle is pi r square. So look here, the magnetic moment is equal to NIA. So magnetic moment will be number of turns are 100. Current flowing through the coil is 2 ampere. Area will be pi r square. Radius is 1 square. Now see, this becomes 200 pi. Now coming to its unit, current into area. So it is ampere meter square. But this isn't complete. We should write the direction here itself. See, it is moving clockwise. So curl the fingers. Thumb gives you the direction. That is minus k cap ampere meter square. Now class, we have studied. If you want to find out the polarity, we know if this is the polarity, how will we get the direction? Clockwise was south polarity, but right now it's not much needed here. It will be needed in your length law of EMI chapter. That time we'll discuss. Let's see this figure. It's a square. So NIA formula remains the same. So magnetic moment will be 100 into 2 into area will be, see, it's a square. So 2 into 2, that becomes 2 square. So magnetic moment will become 800. Now look, this is going anti-clockwise. So anti-clockwise, thumb pointing out. It will be K cap ampere meter square like this. Okay. The questions of magnetic moment will be very easy because they'll be combined with torque. Torque I'll discuss next. A little bit of torque you have to do in this chapter. Most of the portions of the torque we will be doing it in the next chapter. Next chapter you have formula also because your earth magnetism topic is already deleted. Write it down class. I'll discuss the topic torque with you. Please write it. Done class?
Yes, ma'am.
Yes. Have all of you done now? Zainab, what about you? Done? Okay, then let's come to the torque topic. Now here in torque's topic, see, we'll have a coil and there are magnetic field lines that are moving across the coil. So what all things are there? The length of the coil is given to us as L and the breadth of the coil, I have written it opposite. Length will be this. This is the breadth of the coil. This is the length of the coil. Okay, class. And see the plane of the coil that it makes an angle with the magnetic field. See, let's say this is the coil and magnetic field is flowing like this. So this angle that is made between the coil and the magnetic field line, this angle is theta. Okay, this angle is theta here. So this angle that is taken is theta. Angle between what? Between the plane of the coil and the magnetic field line. These purple lines, these are showing the magnetic field lines. Okay, let n be the number of turns. And let's say the current which is flowing through the coil is I. Now let's write down the direction of the forces that are acting. Look, for the first part, the current is coming out of the page. This has been shown a little slanting to you like this. Instead of this, it has been shown like this. So current is coming out and like this. Yes. And magnetic field is towards the right. So I'll take my hand like this. Now see, when I curl my hand towards the magnetic field, where is the magnetic field, class? Magnetic field is towards the right. Where is the thumb pointing? Thumb is pointing upwards. I'm repeating this. Where is the direction? I'll mark this. Let's say A, B, C, D. Focus on A to B, class. Focus on this A to B. In A to B, where is the current flowing? From B to A, outwards. So I've put my hand outwards. Now, where is the magnetic field? Towards the right. Now, if I put my hand like this, I'll not be able to curl it towards the point, right? If I have this, if I curl it towards the point B, so I have to put my hand like this. Current is moving out and point is towards the right. Where is the thumb pointing? Thumb is pointing upwards. Okay, so this is the direction of the force FAP. First, tell me all of you, this force is clear to all? Why the direction is upwards?
Yes, ma'am.
Okay. Class, try and tell me the answer for this one. Now current is moving downwards, magnetic field is still towards the right. Where do you think will the force be? Try it with your right hand only. Don't take the left hand, answer will be opposite. Current is downwards, magnetic field towards the right. Where is your thumb pointing? Not exactly downwards. See, I'll tell you. The current is flowing down. We'll have, see, look at the current. This green part is showing the direction of current. Here, the current is flowing towards the downward side, right? This is towards the downward side. So you will also put the hand downwards. We'll have the hand downwards. Now see, it says magnetic field is towards the right. So I'll have to, if I put it like this, will I be able to curl it towards the right? No. If I put it like this, look class. Now if I curl the finger, where is the thumb pointing? Outwards, right? So here the thumb will point outwards. Current here, magnetic field here, like this you will have. And when you curl the fingers, thumb is pointing outwards. So direction will be outwards for FAD. Now can anyone tell me for CD, this part? Current is flowing inside the page. Magnetic field is downward. This is inside, okay? It was difficult to draw inside in 2 dimensions. So this is inside. Current inside, magnetic field towards the right. What is the direction? Yes, Ibrahim, your answer? Muniba? Current is inwards. Magnetic field is rightwards. So first put your palm inwards. Yes. Ek Muniba. Ibrahim, what about you? Any answers? No. Go outside. See, see. Current is going inside. So I put my hand inside. Current is moving inside the right. See, current is inside. All of you do it right now. Current is inside. So I've put my hand inside. Now I can, how to curl it towards the right side? Magnetic field is towards the right side. If I keep my hand like this, class, and I curl my fingers towards the right, see, hand is pointing inwards. My hand is pointing inwards along the direction of current. Magnetic field is towards the right. I curl my fingers towards the right. Where is the thumb pointing? Downwards. This is downwards. F, D, C. The current is going inwards, so I also keep my hand inwards. So to determine the direction, you can keep it initially like this, you can keep it initially like this, you can keep it initially like this. These are all the possibilities, like this, like this, like this, like this. So which one is correct? If in which you are able to curl the fingers at the point. I like this, I'm not able to curl it towards the right side, right? If I have it like this, I'm not able to curl it towards the right side. Only in this position, I'll be able to curl it towards the right side. Okay, now at least tell this one correctly, class. BC. Current is going up, magnetic field right. Where is your thumb pointing? Yes, Muniba, correct answer. Ibrahim, Zainab, any answers? Take the hand up, curl the fingers towards the right side only. Your fingers should be curled towards the right side. And before curling, ensure your hand is pointing upwards. Any answers, Ibrahim, Zainab? Okay, one is correct, one is incorrect. See, hand is up. This is how we have to put our hand. Where is the magnetic field? Like this? Can I curl it rightwards? No. Can I curl it rightwards? No. Can I curl it towards the right? No. If I put it like this, now I'll be able to curl it towards the right. Where is the thumb pointing? Inside. So thumb is basically pointing inside. And this shows one more fact that all the forces will cancel each other up. Force will cancel the below force. FAD will cancel the FBC. So what do you get here? You will have the net force equal to FAB plus FBC plus FCD plus FDA is equal to 0 because this will cancel this will cancel this. So translational equilibrium. This will be translational equilibrium. Translational equilibrium means the net force is 0. The body will not move forward or backward like this because net force is 0. When the net force is 0, body will not be able to move further. But there is a but here, that is you will have a torque in your system. Okay, there will be torque existing. Torque is the rotational force. So you will have the rotational analog present. Rotational force will be existing. So if rotational force is there, what's the formula of it? Formula is very much similar to the torque in electrostatics that we saw. That time we had P cross E, here it will be M cross P, magnetic moment cross the magnetic field. You open the cross product. First, let me write down what are the variables. This is the torque. M is the magnetic moment. And B is the magnetic field. Isn't it similar to what we have done in electrostatics? P cross E. So here you have M cross B. There you had P cross E. This is M cross B. So this is magnetic field. Now here when you open the dot cross product, you get sine theta. So torque is equal to MB sine theta. MB sine theta. Okay. If n number of turns are there, n number of turns are there, then it becomes, torque becomes n times mv sine theta. And what's the formula of magnetic moment? We know that this magnetic moment is equal to NIA. So torque will be equal to, if I remove this n from here, because n I have already taken here, so I into A. So this becomes n into I into A into B sine theta. NAIB sine theta is the formula of the torque. That's it. You don't have to do any derivation for this. Just remember the formula as it is. Tell me, classes, this torque topic, that's it. That's what you need to know in torque for this chapter. Is it clear to all? Okay. And what about Ibrahim, Muniba? Muniba is here. Ibrahim,
Yes, ma'am.
you've got?
Yes.
Ibrahim, do you have your maths class today?
Yeah, yes, ma'am. 8 o'clock today.
Okay. Please write this class.
No, ma'am.
All right. Now, C class, you have the last topic, conversion of galvanometer into ammeter and or conversion of ammeter into voltmeter. Now, before we begin with this, you should know what a galvanometer is. So you have a device which is known as moving coil galvanometer. So this is how a galvanometer looks, and this must be there at your school. In the physics lab, you must have done experiments in your current, electricity, and moving charges in magnetism chapter. There are practicals which are based on this. So what exactly is a galvanometer? This is a device which is used to detect current. Now, when we say detect current means, does it measure the current or does it tell us what exactly is the amount of current? No. It detects current means it will just tell us whether the current is existing in the system or a no, that no current is existing in the system. Depending on the strength of the current, the deflection will be more. But that won't give you the exact value in amperes. For that, we have a device known as ammeter, which looks similar to this, exactly like this, but has readings which give the exact value of the current which is flowing through the circuit. And a voltmeter is there, which is also a similar device that gives the value of the voltage. So moving coil galvanometer does what? Why we call it as moving coil galvanometer? That I'll tell you in its structure. Basically, just understand this device is known as a galvanometer, and it won't measure the current. Okay, it will just detect the current. See, if this is the device, this is one terminal, this is one terminal, this is the negative terminal. The black one will be the negative terminal. Okay, and this one will be the positive terminal. Now, what is done? Wires are wrapped onto this, and the wires are other part of the wire is no, not even resistance. Resistance also is not shown. It will just tell you whether current is existing or not. So it's a very limited device. It doesn't have much functions. It will just based on the principle of torque, which we have studied, you will see later on. It just tells you whether the current is existing or not. And similarly, the other end of the wire, you will connect it here like this, and the rest of the wires you will connect. For resistance, what you will do, you will connect rheostat to this. So a proper rheostat will be connected to one end, you will bind it, you will bind the other end of the wire like this, and a complete circuit you will form. And when you will switch on the circuit, many times it is required when you just want to know whether a current is coming or not. Especially this is helpful in the Faraday's laws of EMI. That time, it wasn't known whether the magnetic field will help in the current or not. So many experiments were done. I'll teach you those experiments. We have them in our syllabus, that when the magnetic coil is moving, is it producing a current or not? So for that, the galvanometer was used. So you have the galvanometer, and more importantly, the torque is related to your galvanometer. So this is how it will look like. So principle I'll explain later. How much time we have? 10 minutes we have. Let's discuss the structure of it. See, you have two magnets. How are these present? You basically have two permanent bar magnets, not bar magnets, sorry, two permanent magnets are there, and they're radially curved, like they're cut like this in the form of circle. So see, what is this? These are the permanent magnets. Permanent magnets, okay? And what is this? These are the radial curves of it. The radial curves. Why the radial curves? Why is it not straight? Why is it curved? So that the circular coil could be inserted and we could get these magnetic fields radial. Okay. So what are these? These are radial magnetic field lines. Magnetic field lines. So radial magnetic field lines, this often comes in the question class. Construction is a part of your syllabus. Similar diagram is there in your NCERT. So this is an easier one, exactly similar is this. So what is there? So two permanent magnets are there. They are cut radially so that radial magnetic fields can be thrown out. Now here you have a soft iron core present. This is basically a soft iron core which is existing. Now, a core is taken and wires are wrapped onto it. Like say if you have a core like this, wires are wrapped onto it like this. So on the soft iron core, you have copper wire wrapping. Okay. What is this? This is the copper wire wrappings. Why is it? Produce the magnetic field. It provides just to hold the soft iron core. Iron core is also magnetic in nature. We'll study. There are certain substances that can be magnetized. We'll do it in the next chapter. And there is a spring attached. Here you can see there is a spring attached. This is the spring. And here on the spring, what is attached? A pointer is attached. This is known as the pointer. So this is inside. This is covered outside by a scale which was visible to us. This is a scale which is visible to us. This scale is the same scale, this scale. This basically turns. This is the pointer. Inside, this is attached to the soft iron core. I'll show you the actual picture, how it looks like. Wait. See, this is how it really looks like. Can you see this part? These are the radial magnetic fields present. These are the radial magnetic field. Look, the bar magnets are there. They'll provide the radial magnetic field. Here, can you see the circular soft iron core? This part. This is the soft iron core. And these are the wire wrappings here. This is the wire wrapping. And here a spring system is present on which this pointer is attached. Here, this is the pointer. And this is the scale. So again, a covering, lots of coverings are there, insulation coverings, and always notice this is made up of plastic, the outer covering, the plastic wrappings, and make it completely insulated like this. So you have it from inside. If you cut it open, this is how it looks like, but from outside, this is present like this. So this structure, this part which is present and this pointer part, this is a part of our magnetics. That's why we just draw this, the radial magnetic field, the wires, and this circular soft iron cores. These are important for us. And then obviously this pointer will be there, which will be pointing towards the any of the readings of the scale. But this deflection will only occur if there is a torque exists. Okay, that is what is the whole principle. Now let me explain you what's the principle behind it. Okay, then the things you can even note it in the next class, because today Ibrahim has his maths class also, so we have a very less duration, I think 1 hour class only. On Wednesday we have a 2 hours class, so please join, because this will be completed and major portion of magnetism will be done the next chapter. So see, this says if a current carrying coil is placed in magnetic field, current carrying, this is the current carrying coil. It is placed in the magnetic field. How? Because we have put in the magnets intentionally. Then it experiences current dependent torque that we studied. Torque will be there. Current dependent torque, because magnetic field is there. soft iron core is there, magnetic moment will be there. Magnetic moment and magnetic field will lead to torque. That's what we have studied in the formula. So it says when the soft iron core is present in the presence of the magnetic field, it tends to have a torque. Okay. So when the torque is existing, it will produce angular deflection, because what is the function of the torque? To produce angular deflection, to produce rotational effect. So that's why this moves. How is it related to current? When you have current carrying coil is placed. Got it? If the current carrying coil is placed, then only these things will occur. Deflection will occur. If there is no current carrying coil, these wires, these copper wires, they carry the current. Current leads to magnetism. That's what we have seen in the Biot-Savart law. That was the entire Biot-Savart law all about, right? We saw this only, that yes, current carrying wire will definitely produce a magnetic field. So magnetic field will be produced if current carrying coil is there. If the current is not moving, there won't be any torque, there won't be any deflection. So you see no deflection from outside. And when current carrying coil is there, current is there, it produces magnetic field, magnetic moment, they get multiplied and produce torque. Torque produces a deflection. That's why it doesn't tell us the exact reading, but we are able to at least get the value where the current is existing or not. This is it. Tell me, class, is this topic clear to all? Galvanometer at least?
Yeah.
Any doubts in this? Anything you want to ask about galvanometer? Clear? Okay. Do one thing then, start writing from here. No need to make the figures. Just make this figure construction one. Okay, please write it quickly. And keep on texting me done so we can scroll. And on Wednesday, we'll have a 2-hour class. So please join, because major portion of magnetism will be over. The chapter 5th, it's a very small chapter. A soft iron core, basically, it does is it first lets the copper wire get folded. Okay. Second is the soft iron core promotes magnetism because iron has the ability to get magnetized. So that's why the soft iron core has the ability to get magnetized. So it helps in promoting magnetism, the magnetic field, the radial magnetic field that are drawn. Okay.
Yes, ma'am.
Class time is almost up. Will you be able to write this construction part or should I show it in the next class? Because that's what we can do. Is it done? Are you towards the end? Tell me.